Hi, I'm Konstantinos. I'm a senior research scientist at Quantinuum, and I work on quantum computing mostly, and also artificial intelligence at their intersection, but not always only at their intersection, sometimes independently as well. Today I want to focus obviously on the topics here which have to do with longevity, and I'll guide you through some sort of through a collection of projects that I think are related, and I will close with a vision that has to do with AI and technology in general, I will have to say. So first of all, Quantinuum, who are we? We are a full stack integrated quantum company. What does this mean? It means that we have both hardware and software. So yes, quantum computers do exist, but they are still in a prototypical state. They are still pretty small. They can do proof of concept little things, and we're exploring what they can do. But they are getting better. So this is an actual photo of a quantum processor. It literally allows you to store information in excited states of atoms. They're ions trapped in electronic potential wells, and you literally move them around on the chip, and you shoot lasers at them to do logical gates. So a quantum computer works very differently than a classical digital computer. But the idea is the same. You have a problem, you formulate it, you input it, you do some processing, and then you do a readout. It's an inherently probabilistic model of computation, and it's quite different from how we are used to be doing computation today with digital silicon chips. And so we have to, because it's so different, we have to formulate problems also differently in order to design algorithms and solve them. So that graph on the right is showing the increase of a quantity called the quantum volume. It's you don't need to know what it is. It's basically a benchmark. It's a benchmark identifier that shows you how the quality of your quantum computer increases over time. And you see that over the years, the quality of the quantum computers that we are making is doubling or even 10xing every 2 years. So that's a good sign that this technology is scaling. So that's all very well, but what can they do? Why do we need these quantum computers? So this is a very rough landscape of problems from complexity theory. In the green blob, you have all the problems that classical computers can do very fast. That also means that quantum computers can do also very fast, so you don't have to bother with them, because you can do them classically. But this blue blob, called BQP, has all of the problems that quantum can do fast. Fast means in polynomial time. But classically, you struggle. You need exponential time in general, in the worst case. And in this blob, we have problems like simulating molecules in quantum chemistry, or some weird contrived problems from low-dimensional topology that have to do with evaluating invariance of knots and links that no one in the real world cares about, unless your DNA or your proteins are knotted. I've seen some mathematicians write grants motivating this for pure math, but okay. But they are very, very nice proof of concept, well mathematically formulated problems on which you can benchmark your quantum computers, so then that you can go and use them for things where you cannot have strict bounds for performance, for example, like quantum chemistry, where you basically try the best algorithms and heuristically you see how you're doing. And at the top, we have the hardest problems that no one can solve efficiently, not even quantum. But in that blue blob, where we can do something with quantum that we cannot do classically, so that's the green, there's some interesting problems that we think have real-world impact. And the reason we are all here today is longevities, and the way I think about it is, at the same time, it's the longevity of the individual, so that's biology and drugs and all of these nice things, but also the collective, and I hope you all got shell-shocked by the second talk today. That's what the collective here refers to. You know, it's about optimizing the society as a whole. Because what's the point in extending lifespan or even health span if the world is not nice? So an example of a pipeline in drug discovery. I have singled out the first phases where you have quantum chemistry simulations being important in the drug screening, for example, phase. And then there's also later phases where you want to be doing some big data analysis to do some causal discovery, or maybe you want to screen out some molecules with some machine learning on large data sets. So these are applications like quantum chemistry or quantum machine learning where there are niche areas and regimes where quantum algorithms have a theoretical advantage. And these are the areas where we are investigating to see what the quantum computers we have today and the quantum computers we will have in the next 1 or 2 decades, what they can do in practice for these problems. For example, in chemistry, we have the quote from Richard Feynman, which basically goes like, nature is quantum, we all know this. If you're a physicist, you know this. So we should create quantum computers to simulate quantum systems, because simulating them classically is hard. What is a quantum computer? It's a quantum system you can control. And you call it a quantum computer. A physical system you can control is a computer, right? So here is a qualitative plot of algorithms that are used in chemistry. And you see the more accuracy you require in, for example, evaluating the energy of the binding of 2 large molecules, the more accuracy you require, the computational resources scale exponentially. And there are quantum algorithms that promise that you can do this asymptotically faster if you have a fully scalable quantum computer. That algorithm is called quantum phase estimation, QPE, for example. I will not explain to you how it works, but what it does is you give it a molecule and then it says that's the ground state energy of that molecule. And if you have a good model, a good Hamiltonian for that molecule, then you have a good estimate for these energies without you having to go in the lab and actually measure it. So the promise of simulating these things before you go to the lab is you can select what you want to work with in the lab faster, in silico or in Quanto, which happens to be also the name of our quantum chemistry package, product placement. So in quantum chemistry, for example, this is a project we did with Roche, which was basically this. You go to some big complex, you identify the part of the complex that you want to model, and it will be the one that the classical algorithms are struggling with. This part of the molecule will be the one where the electrons are strongly correlated. So you have exponentially many configurations to take into account, and that's what the quantum computer is there for. So in this project, what we did is we tried different fragmentation strategies, that is how to break up the molecule in different ways, such that you optimize classically which part of the molecule you should outsource to the quantum computer and which part of the molecule you should outsource to the classical computer. And then we see how this compares with the state of the art. We do resource estimation, and then basically we do a proof of concept for small molecules and estimate what the resources would be for larger and larger molecules. So this type of work is what we think and what our clients also think will have some impact in maybe the drug design pipeline. So this contributes to the individual longevity angle that I was talking about before. When it comes to the higher level societal angle, we are looking at things that have to do more with material design. So from quantum chemistry simulations, you can identify which materials have better properties in terms of capturing, for example, CO2, right? So there is a project we did with Total Energies, which was about carbon capture. And again, it's the same idea. You have a molecule or 2 molecules, and you want to see what's the energy in which they lock in and bind. And again, a quantum computer can accelerate these things if you had one, right? We don't have one yet that is fully scalable, but if you had a fully scalable one, you would have an advantage here. In the prototypical quantum computer we have today, we are using simplified versions of these molecules, but we know how we would scale both the hardware, the algorithms, the software that handles it, and how we would scale the problem sizes in order to solve the more complicated problems. So you see, of course, we need to build the hardware, and we're working hard on doing that. But at the same time, we're exploring use cases for this to identify what we would use these quantum computers if we get them by the end of the decade, which is what the roadmap tells us. Now, the other aspect I talked about is not so much in simulating the physics, but it's in enhancing the machine learning capabilities of some classical algorithms that exist today. So, an important thing is doing causal discovery in general. Causal discovery in its full form is very, very hard, even for quantum computers. But some things that there are some things that you can do which are more specialized. For example, variational inference. You have a bunch of observed variables, like for example symptoms, and you have some hidden variables you don't have access to, either because you cannot do some experiments due to some ethical constraints, like for example cause some people to smoke, like force feed them cigarettes to see what happens to them. But you just have data, right? And you want to see causal connections between them. And we have this very nice paper by our quantum machine learning team where they examined how you can apply variational quantum computers, parameterized quantum circuits, instead of neural networks, and use them in machine learning pipelines to solve these problems. Now, asterisk, this doesn't have a proven quantum advantage, so you have to examine case by case heuristically. But sometimes these quantum circuits have nice properties. For example, the number of trainable parameters will be much smaller, and things like that. Another line of work we did with parameterized quantum circuits as machine learning models has to do with language processing. We started with natural language processing, so I can classify, for example, movie reviews using quantum computers, which is not probably the best case for them, but it was pretty fun. But you know, you say, okay, what else do I know that has an alphabet, words, syntax, and so on? Biosequences. And indeed, there's a lot of NLP, machine learning algorithms, like state-of-the-art today is transformers, that are used in language modeling in quotes, sequences of proteins or DNA or RNA, and then using them to predict. Basically, these algorithms predict the next token or classify sequences, and that's what you use them for in bioinformatics as well. So here we had a project with Amgen and some other independent project that I did with my team, where we basically found some RNA datasets online, open source, and the whole idea is classifying some sequences and seeing the benefits in these quantum classifiers versus their classical counterparts. And again, we saw some cute benefits like a smaller number of parameters, faster training, things like this. Again, no proof of quantum advantage asymptotically, because we're going case by case, because that's how machine learning works. However, there is an aspect of machine learning which has provable quantum advantage, which is very interesting, and goes under the slogan and falls under the category of small data, big compute. So for example, in topological data analysis, what you have is a lot of data in a lot of dimensions. So imagine a point cloud, and then what you want to do is essentially extract the shape of data. So what people do is they do something called persistent homology, which essentially what it does is it counts how many holes there exist in your data of whatever dimension. So there are these things called Betty numbers. So Betty number subscript k equal is an integer, and it equals the number of holes in dimension k that your dataset has. So apparently this is useful for various multi-omic datasets that I was very happy to find this is the case. Apparently you can have these datasets, and the topology of these datasets tell you and give you a lot of information about biological functions or pathways and various things that are useful for biologists, geneticists, people who try to do drug discovery, and various things that we all care about in this group here. So how this works is basically there is a whole pipeline where we have taken these algorithms that suppose that a quantum computer fully scalable exists, and try to hack it down so that these algorithms outsource as much as possible of the compute to classical algorithms, and keep only the essential parts that you cannot outsource to classical on on the quantum computer, and then we do resource estimation, again, as for chemistry, to see how to construct our hardware so that these problems can fit there, while at the same time trying to run classical algorithms to see and confirm that it's actually a hard problem to solve. So in this paper you can see a whole pipeline for how this works, and we are actually working with real-world multi-omic datasets on doing this and extracting this topological information. Also, we have the flexibility to change what type of topological information we want to extract from these datasets, which, also in conversation with the domain experts from biology and bioinformatics and so on, maybe they come up with a suggestion. Hey, we are interested in this and this topological property, and then we try to see if we can extract it from the quantum algorithm. And then I'm going to move away from quantum and close with something which is basically a very sci-fi project, but we have started making it concrete. So I truly believe in science. And I think we should do it better. I think science is very hard. I think humans are smart, but not that smart. I mean, we're smart enough to do cool stuff, but not smart enough to, stop climate change, for example. Apparently, we cannot coordinate. I think we need help. And I think things are science fiction until they aren't. And when I say we need help, I think we need to build some intelligence to help us do some science. So, of course, there is a super sci-fi dream of having a fully automated scientist, but the more grounded version of this is we can use the machine learning technology that exists today and works today, for example, large-scale reinforcement learning or large language models, to help with curating the literature, forming and testing hypotheses faster in simulation, and things like that. Of course, I understand that training large AI models emits a lot of CO2, right? So how do you prioritize? Well, I don't know. We need to think here, right? There's many things that we are wasting money on, in my opinion, in my humble opinion. We should maybe spend it on this, cost benefit. Otherwise, stop doing anything. Stop everything. That's also a solution, but we don't want to do this. So I have, I've done a lot of thinking here, and I have come to the conclusion that we need to also be doing steering some of the AI research applied to science. And I actually have seen some prominent figures like Eric Schmidt giving funds into AI for science specifically with Future House. I have seen what DeepMind is doing and spinning out isomorphic, which specifically focuses on biology. And what I'm suggesting here is that we take all of these approaches and we make them generic for all of science, and basically automate what humans do or work with humans and build towards something that scales better. So I'm going to leave you with this high-level vision, but also remind you that there are things that work today, and there's a lot of scientists that work very hard to advance these technologies, and they all do believe that they're doing it for good. And I am one of them. So thank you.
Thank you so much, Konstantinos. Now, I actually understood some of that. I don't... some. I said that this time last year you got into some of the quantum stuff, and I think I got to about slide 3, and then... But I've read that if you actually think you understand quantum anything, you obviously don't. So that puts me in the place where I've definitely understood it, because I don't. The uncertainty. Anyway, so questions on... and I loved your optimism that there is something actually that...
Apparently optimists live longer, right?
Exactly. So questions for... Konstantinos, yes.
Yes.
So just to the end of your talk, I don't think it's wild thinking at all.
Yeah.
To want to make the science of biology much more efficient.
Yeah.
It's desperately frustrating to anyone working in the field that our own linear thinking is a massive barrier to regression that almost I suspect the majority of experiments that are run are either imperfect and therefore irrelevant, or they are redundant and unnecessary. So I completely and utterly agree, that's all I can say. And in fact, twice in my career in big pharma companies, I've hired somebody to come and form an AI group embedded deep in drug discovery. Unfortunately, they're so good that they got promoted and got better jobs and ended up doing other things instead, and I still failed to get some to do it. But of course, there are many companies in the field, so please continue to be passionate and help us.
Well, there's a lot. No, behind Richard, yes. Thank you.
My name is Lee from Action Against Age-Related Macular Degeneration. Very interesting talk, thank you so much. So I was thinking that when you mentioned the Betty holes, right, whether that could be a better, or actually the transformational thing that can help us understand about it. Because as our colleague here mentioned, we're always looking at end stage, even at binding of compounds. We either look at the beginning or the end of the binding state. We never look at the transition state, which is what we should be aiming for. So in that sense, when you look at gaps, can you apply this technology to actually find things we should have considered, but have not before? So exploring your Betty holes into a way that is actually explainable. So to guide us to where to go.
I have heard the topological data analysis experts say and claim that that type of machine learning is more explainable than just applying some deep learning pipeline to some data, because in order to put your data in this high-dimensional space, you have done some curation and you know what they mean. But beyond that, I don't know what else to say without going into some explainability tangent for reality. That's like a whole hour discussion there. But for the quantum simulation aspect from chemistry that you mentioned, so actually in quantum chemistry, to get the ground state of molecules, there's really good classical heuristics, like tensor network techniques. But to do dynamics in general is harder. So real-time time evolutions of reactions or time evolutions in condensed matter physics, that's where really you need to explore the full state space. And if you have a formulation of the problem that allows you to model the dynamics and outsource it to a quantum device, then yes, you would be extracting more information. But we can talk later for more details, so I don't say something that doesn't mean anything.
Okay, now there was a flurry of questions around there. And right, you can each have like 30 seconds, so first and then second, thank you.
Thank you so much, Alexander Gamberti. Question for you. Can you speak, a lot of the things are still prototypical. Can you speak to some timelines, like for example for the total energies case with carbon capture? And second, you spoke about, you know that you can scale the models, the hardware, the algorithms, the software, the hardware. How do you test? Can you speak a bit about how you test and scaling? Because I think that's quite a big challenge.
So for the hardware, it's easier to answer this because it's an engineering challenge to scale up these ion traps and connect them together and move ions between them and basically scale the whole quantum chip. And then there are rigorous benchmarks we can do to check the quality of the quantum computer and check that it operates how we think it operates. When you scale up the model, basically that's not really a problem, right? You have a Hamiltonian that describes the molecule the best that you know, right? And then you just compile the Hamiltonian into a quantum program and run it. That's not a problem. Now, you might want to go into a loop of iterating over your model from experimental output after you do your simulation. But if you don't have a quantum computer, you cannot do this. The pessimistic message here is that quantum computers are very hard to build. So we won't have them tomorrow. We will have them by the end of the decade, right? But it won't be like a 0-1, like I have them today, I don't have them today, I have them tomorrow. They just grow and evolve. And the error correction that you have to do becomes more and more sophisticated. So it's not fully noisy or fully error corrected. So I cannot give you a very good timeline. I can tell you that by the end of the decade, we will have order 10 of unsimulable machines, and we will be able to run some of these hard simulations on them. Now, I ended this slide with the reminder that we have a lot of algorithms today that actually work today on GPUs and TPUs and FPGAs and whatever, and CPUs and whatever, or a Commodore 64 if you want. But we are using them to sell people ads.
Yeah.
Let's do something else.
Yeah. I can.